All right, y'all, we're going to go ahead and start with a example with kinematics in the vertical direction. We'll have some free fall. We'll need to include the acceleration of gravity. Let's just jump right into it. While hiking, Aya comes across a small hole in the ground that appears to open into a large cave below. She recently learned about free fall in her physics class and drops a coin into the hole to try to figure out how deep the cave is. She times the coin as it falls using her phone and hears the coin hit the ground 2.1 seconds later. So let's see if we can solve this. The first thing I'm going to do is I'm going to draw a picture because that's going to help me out a little bit. So we've got a hole which opens up into some kind of cave below, and that's basically it. So she starts with the coin up here at the top of the hole, and she drops it down to the bottom of the cave, and that takes 2.1 seconds. Now that doesn't feel like a lot of information, but if we put it into our table and write down all the information we know, then look what we see. So we've got x naught, we've got x, we've got v naught, v, a, and t. We go ahead and put into that, we're going to start at the height of the ground, which I'm going to go ahead and call that 0. Okay. Then the bottom, the final height, will be right before it strikes the ground. So right before it strikes the ground, I'm just going to put x. That's actually what I'm looking for, how deep the cave is. So hopefully we'll get that. V naught is the initial velocity. The initial velocity is how fast it's moving right here as she drops it. Not when she's holding it, but the instant she lets go, we're going to say that's close enough to 0 that we're going to put 0 there. The final V is the speed right as it hits the ground. I don't know what that is, so I'm not going to worry about it. Acceleration, well, acceleration is, well, as it's dropping, the only force acting on the rock is gravity. And so therefore it will be the acceleration of gravity, the negative 9.8 meters per second squared. Now, I'm going to go ahead and put my units in these just so that we can make sure that we're seeing that. And then, of course, the final time is 2.1 seconds. That's it. So with this, we have everything except for the height that we're looking for, that depth, and v. So what do? We choose an equation that doesn't have v in it. And so in order to do that, we're going to use the equation that looks like this. X equals x naught plus v naught t plus 1/2 at squared. And we go ahead and put the numbers in. So x equals 0 plus 0t. Sorry, that was 2.1. Doesn't matter. It's going to be multiplied by 0 anyway. Plus 1/2 times the acceleration, which is negative 9.8, times the time, which is 2.1 seconds. Now, you'll notice I didn't put the units in here. That's because all of my units here are what we call SI, standard, the Sistema Internacional. I have no idea how to say it. Don't mess with me. All right, we got meters and we got seconds. That's all that matters. So when I work this out, I should be able to then calculate and get that x equals negative 21.6 because it's a distance. That's meters. Now, I did get negative because this will always give me displacement, and the displacement was downwards. You can just put for the height or the depth that it is 21.6 meters deep. So that's the letter A. Now, letter B now asks, how fast is the rock falling? All right. Well, I can actually use the same table as before, right? Because I'm still starting at the same point, and I'm still using the same ending point right before it hits the ground. And so I can use all of the same information that I had before, except now I also have that x is negative 21.6 meters. So now I'm finding how fast as it hits the ground. So all I need here is v, which means I can use any of the equations, right? Any of them that have v in it. Obviously, I don't want to use this one again because that doesn't have v in it, but either of the other two is fine. I'm going to choose the one that looks a little bit easier, which is v equals v naught plus a t. And so I should be able to calculate that. V naught was 0, acceleration was negative 9.8, and of course time was 2.1 seconds. And if I do that, I should end up getting negative 20.6 meters per second. And so again, I got a negative because it's moving down at that point. How fast was it going? It was going 20.6 meters per second. No problem. Now the last question here is letter C. She learns that the actual depth is only 20 meters. Why might this be different than what she calculated. I was going to say there's no right or wrong answers, but there's definitely some wrong answers, but there's a lot of right answers here. You could say any number of things. You could say, well, perhaps when she dropped it, she didn't drop it from the height of the hole. Maybe she was holding it above the ground when she dropped it, right? That would end up with her having a larger height than is actually the depth of the cave. Perhaps it's because we ignored air resistance, right? Maybe ignoring air resistance would slow it down and make it seem like it's taking longer. Well, it would take longer than it should without. And so if it takes longer, then we'd end up calculating a larger height. So maybe that was it. Another interesting idea is as it goes down, the rock is going to, the coin's going to hit the bottom, but then the sound has to travel back up to where she could hear it and stop the stopwatch. So maybe that's it. Maybe it's because we ignored the time that it took the sound to travel up. Sound travels pretty fast, but it's not necessarily negligible. Another option could possibly be, maybe she just timed it wrong, right? It doesn't say anything about her using a camera wouldn't do any good anyway, because maybe she can't see the bottom of the thing. But, her timing could have been off, and that could have resulted in a slightly different answer. So lots and lots and lots of good reasons as to why she might get a different number than the actual height. So that's it. Hopefully that makes sense and you got some different ideas there. Let's move on to the next question. All right, here we go. We got a new question about Sophia. She's locked out of the house and wants to throw a rock up at her sister's window on the third floor of their villa. The third floor window is 6.7 meters off the ground. We're going to ignore her height. We are going to simplify it a little bit by just ignoring Sophia's height here as we go. And here we go. So what is the minimum velocity Sophia must throw the rock at for it to reach the window? Again, just like the last one, we may feel like there's not enough information here, that we're missing some stuff out. But, let's go ahead. Let's go ahead and have Sophia here. She's going to throw the rock up so it hopefully just reaches the window there. All right. What information do we have? Well, we're going to add that into our table here. So x naught, x, v naught, v, a, and t. We're going to start with our initial position down here at the ground. Like I said, we're going to ignore her height just a little bit here. For x, we're going to put in the height of the window, which we actually know that's 6.7 meters. So our initial, remember the 0 is just initial. That's time 0. So at time 0, the beginning, 0 height, and then we've got a final height up there. Initial velocity, we don't know that, but that's actually what we're looking for, right? Now, don't get confused. The initial velocity is not when she's holding it. Remember, kinematics only works if the acceleration is constant. And when the ball is flying through the air, that will be a different acceleration than when she's throwing it, right? When she's throwing it, it's actually accelerating upwards. Once it goes up in the air, the acceleration is the acceleration of gravity, which is downwards, causing it to slow down. So those are two different situations there. Don't put those both in the same table. All right, so our final velocity, now this is a challenging one because in order for this to be the minimum speed, we want it to just barely get up to the window, which means its speed right at the window would be 0 or very, very close to it. All right, notice that I'm putting everything in meters and seconds, right? And so there we've got the acceleration, which as the ball is flowing, as the rock is flowing through the air, it's going to be a negative 9.8 meters per second squared. That's our acceleration. And we don't have time, so we're not going to worry about it for now. So now we do need to try to pick an equation that's going to allow us to solve for that. So that's going to be the one that doesn't have time in it. So v squared equals v naught squared plus 2a x minus x naught. And then we should just be able to put everything in there. Our final velocity is 0. Our initial velocity is what we're solving for there. 2 times negative 9.8 times x, which was 6.7 minus 0. And you should be able to multiply those, put those together there. I'm going to end up getting negative 131.32. So 0 equals v naught squared minus 131.32. And then we can add this over to the other side. So we'll have 131.32 equals v naught squared, and square root both sides, and we should get that our initial velocity is equal to 11.5 meters per second. So she's got to throw it at a decent speed in order to get it to just barely reach the window. Now, she can throw it harder than that. If she throws it harder than that, it'll make it to the window. It's just it'll have a little bit higher speed when it gets there. Throw it too hard, you could break the window. So that's why we're looking for a minimum speed. All right, so that's letter A. Letter A isn't too bad. Moving on, it then gives us a different scenario, different situation, different information. Her sister is annoyed by all the rocks striking her window and decides to throw a water balloon down at Sophia. She's able to throw the balloon with a speed of 4.2 meters per second. If she throws it straight down, with what speed will it reach the ground? So let's go ahead. We're going to go ahead and change our picture here. It doesn't look like it's going to let me do that. So what we're going to do is we're just going to kind of erase this here. So we'll go white. All right. So we're going to erase the picture we have here. So now, instead of her throwing it up, we are now going to have her throwing it down. So the sister at the window is going to throw it straight down. She's going to be trying to hit Sophia down there. All right. So let's go ahead. This is obviously a new situation, a new initial and final point, new information. So we're going to need to create a new table here. X naught, X, V naught, V, A, and T. This time I'm actually going to start up here. Same height, so 6.7 meters. So I'm going to put 6.7 meters there. The final height would be, it says, with what speed will it reach the ground? So if she misses Sophia, it goes all the way down to the ground. Then we know that our final height is going to be 0 as it reaches the ground. The initial speed, that's that 4.2 that we talked about. So that's how fast she can throw it. The final speed, that's what we're looking for, right? That's the question, is with what speed will it reach the ground? So that's my V. And we, of course, know that acceleration is negative 9.8 meters per second squared. Now, again, don't get confused. A lot of students think, but didn't she throw it down? Shouldn't there be more acceleration? Well, there was more acceleration when she was throwing it. When she held it in her hand and launched it downwards, that was a different acceleration. Once she releases it, it has a speed of 4.2, and the only force acting on that the water balloon now, hopefully she's not throwing rocks down at her sister. The only thing, but of course water balloons are fine. The only thing acting on the water balloon as it falls down is gravity. And so gravity is the acceleration there, negative 9.8. So we don't need the time here. We'll go ahead and ignore the time. And, I do need to, my initial velocity, I'm going to make that a negative 4.2. Now, the reason why is because I'm throwing it down, and because she's throwing it down, that initial velocity should be negative. That's going to be important because the next question asks, well, what if she throws it up? And so we'll need to do the same thing with a positive. We can go ahead, put in some numbers here. Again, we don't have time, so let's use the equation that doesn't require time. So v squared equals v naught squared plus 2a x minus x naught. And our final speed, that's what we're looking for. The initial speed was negative 4.2 squared plus 2 times the acceleration of negative 9.8 times x, which was 0, minus 6.7. I can calculate each of these things. The 4.2 squared, type all this into your calculator. I'm not going to take time to do that. When you type all that in, you should hopefully get 148.96, just like that. And we end up then square rooting both sides, and we should get that V equals positive or negative 12.2 meters per second. The velocity should be negative because it's going down, but the question is what speed, so you could just say 12.2 meters per second. All right, but I just want to remind you that yes, velocity should be negative there because it's moving downward. Note that it is faster than this one, and you may think, but didn't she throw it down with a lot more speed? Yeah, but it's going to get down to the ground a lot faster, which means it has less time to accelerate. So yeah, it's a higher speed, not that significant, but it's definitely higher than it was what Sophia needed to get the ball up to the window. All right. Part C, we're moving on here. Part C then says, well, what if she throws it up? So instead of throwing it down, so now I'm going back to my picture over here, she throws it up with a speed of 4.2 meters per second. And so it goes up, and then it comes back down. So now what will the speed be when it reaches the ground? Well, you could make a table here. And in fact, that's what I'm going to do. But, my table is going to be exactly the same, except my initial velocity here, instead of being negative 4.2, it's going to be positive 4.2 because I'm throwing it upwards. So let's make that table. So hopefully it looks something like that. When you put that in again, we're looking for that final speed, the V right before it hits the ground. That V again, we're not looking at t, we don't know time, so choose the equation without time. It's going to end up being exactly the same equation again, right? So we're going to go V squared equals V naught squared plus 2ax minus x naught. And when we work that out, it should look very, very similar, except this time I'm going to have the 4.2 be positive. You know what? It really doesn't matter because it's going to be squared. And so I should get actually exactly the same thing. You work that out, you end up getting that v squared equals 148.96. Should be exactly the same as last time. And when I square root it again, I should end up getting that negative 12.2 meters per second. Again, you should get positive or negative. We understand that because it's moving down at the end, it's a negative 12.2. Now, hopefully that's not too surprising. It may be, because you may be wondering, well, doesn't it take more time, or all these different things. But remember, when the ball goes up, let me go highlight this. When the water balloon goes up, gravity is causing it to slow down with a very specific rate, right? Gravity is causing it to slow down, slow down, slow down for that specific height. As it comes back down, gravity is causing it to accelerate with the same acceleration that was making it slow down before, over the same distance. And so therefore, when it gets back to the point that it started at, when it gets back to the window after going up and coming down, it will have the same speed as it had when it was thrown up in the air. And so from that point on, it's identical. The difference is it's going to take a little bit longer, right? And that's what we're going to find in D. Her sister decides to give her a fighting chance, so she throws the balloon straight up in the air. And the question is, how much time does Sophia have to get out of the way before it crashes down on her if she is 1.65 meters tall? So we are going to need one more table. So here we go. Let's change our color again. Lovely. We're going to go with purple. So for letter D, this time she is going to throw it up in the air again. X naught, X, V naught, V, A, and T. So X naught is going to be the height of the window there. The height of the window is still 6.7 meters. The final height, that X, is going to be Sophia's height, because the question is, how much time does she have before it hits her? If we wait till it hits the ground, it's already too late. So we're going to put in for the X our new height of 1.65 meters. Our initial velocity, she's still throwing it up with a speed of 4.2 meters per second. Our final velocity, we don't know at this point, because it's not the final when it hits the ground, it's the final when it reaches her. The acceleration is still negative 9.8 meters per second squared, and we are looking for the time this time. So we're not going to use the same equation again. If I use the same equation, then I wouldn't be able to solve. That's going to give me V. So instead, I want something with T. I need something that does not have V in it, and so therefore, I'm going to go with that X equals X naught plus V naught T plus 1/2 AT squared. So X is going to be 1.65 which is going to be equal to 6.7 plus v naught, which is 4.2 t, plus 1/2 times the acceleration, which is negative 9.8, times the time squared. So that gives me a quadratic. You can solve that using quadratic formula or calculator or whatever. I won't give you one on an assessment where you have to be able to solve a quadratic, but here, punch it into Desmos, punch it in your calculator, whatever you need to be able to solve that. Hopefully, you'll end up getting that time is equal to 1.65 seconds. And so she's got a decent amount of time to get out of the way. So hopefully she doesn't get too wet by the water balloon. Anyway, that is the answer to the question. I hope that was helpful, and I'll see you next class.